Right, beta is the minimum
Yeah.
element.
Right. Okay. In any case, the point is there is some element below alpha, or below any given property, which is that elemental minimal, such that below that there is not that property. And here's the fun and wacky thing: you go down far enough, you get the void. So whatever it is, ultimately the void doesn't share that property. So this is going to be definitely true. But where it gets interesting is there are times that this occurs above the void. Above the void, right? So it's not just, oh yeah, eventually you'll get down to the void, so it's not going to have that property. There are actual sets that have that property well before the void. Like the properties of being a nation sorted out of United, we always use this, and by we I mean I always use this, nation. Take the set of the United Nations, right, in its totality. Now apply a property which is the set of nations, right? You'll notice that it's very quickly, except for like weird pseudo-nations like, I don't know, Indonesia that is, what's the word I'm looking for? A prison house of nations, right? For every other nation, there's no nation below that, right? The United Nations, sorted for the property of nations, that very first level of the United States, Canada, Mexico, Panama, Haiti, Jamaica, Peru, that is the E-minimal set, right? The E-minimal elements under which there exists no other nations. Again, there are some exceptions, right? But what's the nation to which, belongs to which it is the United States? That was incoherent. Again, very tired.
The answer is all of them.
Yeah, okay.
But the reason there are exceptions is because he's dealing here specifically with natural multiples.
Right.
And of course, states and nations are not natural multiples.
Exactly.
So, but dealing with natural multiples, this is going to be much more rigorous.
The way I understand it is there's an eventual terminating point once you go through this sort of sequence function, if you will. I don't know what I was trying to say there, but I'm trying to roughly conceptualize what I got out of it. I don't know.
Well, fair enough.
I mean, to a large extent, all he's doing is mentioning what is an ontological mathematical theorem. You can prove this, given the axiom of foundation. You can prove this. So all we need to know is that. Right? He's not going to draw any gigantic political consequences from this theorem, but he is going to use this theorem over and over and over again to prove things that will have all kinds of interesting implications.
Right. And again, we're dealing with ontology, not politics here. I'm just using that as an example. So. Okay, so does everyone understand this E-minimal sort of property? Or, it's property. Okay, so again, because of the transitivity of ordinals, every ordinal either belongs to another ordinal or that ordinal belongs to it. Moreover, because this is true, there are no voids in nature. So basically what he's saying, right, is for every ordinal, everything underneath it belongs or is included, right? So if it is an ordinal, and there is another ordinal, right, everything beneath each of those ordinals is going to belong and include it, or belong and be included to it. So if there's a bigger ordinal, every single ordinal beneath it, right, will belong and include it, including that other ordinal, or that other ordinal will be the bigger ordinal, such that it will have the other ordinal belong and include it. Does that make sense? Okay. So again, but there's no way to insert something in between the ordinals, right? Because again, this property of transitivity and normality, which are again definition.
In between the ordered ordinals.
The ordinals, yeah.
There may be an ordinal between this ordinal and this ordinal, but it's always going to be an ordinal is the point.
Right. There'll be no gap.
Right.
Okay. Unlike excrescence of the state.
Any historical.
Yeah. So Badiou supposes two ordinals are not connected. So what's important here is this is a supposition, right? And so this is actually going to be proven negative, but it's a supposition. So Badiou supposes that there are two ordinals that are not connected. And this is 137 and 138. Because every ordinal is has an E-minimal element such that this minimal element is not a part of the other, and there exists an E-minimal property for that very property, Badiou deduces the impossibility of this situation. So basically what we have is we presuppose that there's two ordinals that are not part of each other, right? Well, what they'll have to have is they'll have to have this E-minimal property of being an ordinal, for one. But then they also have to have this additional property of not being part of each other. Well, the problem is, for this property, there exists underneath it another property. Let's actually go to the book, because
We were playing with lambda and delta.
yeah, this is the
This
delta.
is proof on 137, 138.
I'm just going to read it.
I mean, did anyone not follow the proof?
Or
It's
is everyone-
pretty straight, rigorous proof.
Yeah.
So everyone's good on that? Does anyone want me to go over it or go over it for the people at home? Okay, well, he presupposes the ordinal and then proves that would entail that they later would have to be belong to each other and ergo be included because they're ordinals. Okay, so 4, the ultimate natural element, the unique atom, this is section 4. For any property, let's see. For any property, it determines a unique E-minimal element. For any given two ordinals, either it contains that element, and thus is quote-unquote smaller, or does not, in which case it is itself the E-minimal element. So the basic idea is this, going back to our little ordinal chart. So here's phi, right? This is going to, psi, sorry. This is psi. And in this case, it has a unique E-minimal, or it's not unique at this point, but it has this E-minimal element. So either it contains this element, and then we also have this smaller element, or it does not contain this E element, which means it's at the very limit itself, right? Below beta, it doesn't contain this E-minimal element, which is what, sorry, just lost my train of thought here. So it's not the case, sorry, I got like 4 hours of sleep last night. And given two ordinals, it contains a smaller.
The last paragraph on 138 is where it just gives a very short proof.
Yeah.
That beta is a unique element. In other words, there can't be two ordinals that are minimal. There's got to be one actual unique minimal ordinal.
Right, because anything's
And you can prove it just
smaller.
by extensionality.
yeah,
Right.
because it would have to if it's C-minimal, yeah, it would have to have the
So-
same.
But that will be crucial later once he gets the axiom of foundation on the table, because then that's going to be the atom from which you can construct.
Yeah.
But we do need to recognize that as unique and not just that there are minimal ones. There is a minimal one.
Right. For a given ordinal, because if it's not.
For a given property.
Yeah. That's also an important distinction. Is that under some properties, certain things will be minimal, and under other properties, they will not. Which seems self-evident, but it's worth pointing. Okay, let's move on. Ordinal is a number, which is a name. Okay, so every ordinal can be understood as a continuation of the previous chain of quote-unquote smaller elements, but is also, this is going to sound weird, but also a rupture in an independent set. So this is, I kind of refer to this in a sort of weird conceptualization, but there's no time in set theory, right? So one of the ways in which we would like to think of ordinals is as a process, right? That it's a process of smaller ordinals getting into bigger ordinals, et cetera, et cetera, et cetera, et cetera. But the problem is this is not a process because each ordinal exists independent of any other ordinal. And so what we can't do is conceptualize it in and of itself as a series, right? Each ordinal is itself an independent set. So the important thing, I think, of Badiou making a point to mention this, is what we shouldn't do is, for all of our languages or functions, we should not view them as rendering an intrinsic difference or even a substantive difference, right? Set theory is above all a theory of indifference, and there's the indifference of the pure multiple as such that two ordinals that are next to each other are themselves not, in a certain sense, not linked, or are only linked by the principle of belonging. Just as a non-ordinal set that contains a bunch of other elements would be. Does that make sense? And why that's conceptually